So some announcements about what's coming up. Quiz 2, your memorized rules quiz is due today. So just put that in your folder. If you handed it in early, it's still in the folder and I haven't looked at it yet, just leave it there. And then there's no class Monday anywhere at GCC. So we will meet again on Wednesday when Project 2 is due and Project 3 will be assigned. And then after that, in the following weeks, we've got another quiz and a test coming up. All right, so in this class, we're going to learn the technique of integration by substitution. This technique is the most important integration technique by far. We're going to spend 2 days on it. We're going to learn many techniques for finding antiderivatives this semester. The most widely used of the techniques that we'll learn is the one we cover today and next class, substitution. In the same way that the chain rule allowed us to differentiate many new kinds of functions last semester, the substitution method is going to allow us to anti-differentiate many new functions this semester. So spend some time in the coming weeks reviewing material from this section. If you don't get good at substitution, much of this semester will be tough. No pressure. So many integrals that we will encounter will not initially be one of the few forms that we've studied so far. So right now we can do really basic going backwards antiderivatives, right? So if the function is simple enough, we can say I know a function whose derivative is that, so I can go backwards and get an antiderivative. But there's a powerful technique known as U substitution that we're going to convert, that can convert a bunch of unrecognizable integrals into easy-ish integrals. All right, so I changed my mind about the example here. We're going to just get rid of this first term. Ignore that. So we're just taking the integral of 9x minus 3 over x squared plus 1 dx. And we're going to use substitution. Don't worry about frantically writing out all the steps here. The step-by-step process is on a reference sheet near the beginning of the packet. I'll show you in a couple minutes. First, we're going to do a little bit of side algebra. I'm not doing any calculus right now. I just want to look at 9x minus 3 over x squared plus 1. And I want to try to break it into something simpler. Right, so first I look at this thing and I go, okay, if I'm trying to integrate that, first thing I should do is look at my table of integrals and see, do I have anything in my really simple list of integrals that looks like that? Right? So I'm going to go back to the beginning here. Reference sheet, where is it? Here we go, integration formulas reference sheet. So anything. Oh, I've got, oh, there's an extra U right there. Look at that typo. Typo in your packet. Okay, so I have something with a 1 plus U squared in the denominator, 1 plus something squared in the denominator, but you can only use that rule where the integral of 1 over 1 plus U squared du is the arctan of U plus C. You can only use that if your numerator is a 1, right? My numerator is 9x minus 3, right? So I can't use that rule because it's too different. And there's nothing else in the table that might possibly help me. So I'm going to try to use some algebra first. To try to simplify the integrand before I integrate. Okay, here we go. All right, so I'm going to break this into 2 fractions. So I want you to tell me if this is allowed. 9x over x squared plus 1 minus 3 over x squared plus 1. Allowed. How come? It's the same denominator, so if I were to go backwards, I could add them together because they have the same denominator. So yeah, that's allowed. Okay. All right, so I broke my fraction into 2 fractions. So that means I can break my integral into two integrals. This is going to become the integral of 9x over x squared plus 1 dx minus the integral of 3 over x squared plus 1 dx. Okay, so that was one of our rules about integrals. Actually, maybe I should write it not separated first. Okay, so I broke my initial fraction into two fractions. And then we had this rule about integrals that when you're taking the integral of a sum or a difference, you can break it into two integrals. Okay. All right, and then we have that rule about constants. What if you have a constant coefficient? What are you allowed to do with that? Yeah, you can pull it right out of the integral, if you remember. So, but it only works with constants. You can't pull any variables out. But I could pull the 9 out, and I could pull the 3 out. Okay, you can just pull it right through the integral. So this becomes 9 times the integral of x over x squared plus 1 dx minus 3 times the integral of 1 over x squared plus 1 dx. All right, one of those is a basic antiderivative rule from your table. What is it? Which one? The second one. And what is the antiderivative of 1 over x squared plus 1? Arctan. Yeah, the derivative of arctan x is 1 over x squared plus 1. So this one on the right, we can do right away, nothing fancy. All right, so I'm just going to copy the one on the left for now. And then I have minus 3 arctan x plus c. Okay, so this is in table of integrals. Okay, that's just one of the integrals that we know. We know a function whose derivative is 1 over x squared plus 1. All right, now the one on the left, the integral of x over x squared plus 1, is not that much more complicated. But it's going to require a more sophisticated technique. All right, so I'm just going to show you what the technique is, and then I will afterwards explain how I chose, how the choices why I made the choices I made. All right, so this is called U substitution. So we're going to substitute a U. Okay, so over here, I'm going to write out my substitutions. So I'm going to let U be x squared plus 1. All right, so that means du dx is what? 2x. If you solve this equation for dx, what do you get? Pretend du dx is a fraction and you solve for dx. Du over 2x. Good. All right, so now I'm going to take all that information and I'm going to substitute into the integral that I have. Anything that can substitute exactly, I'm going to substitute. So I'm going to replace the x squared plus 1 with a u, and I'm going to replace the dx with a du over 2x. All right, so this becomes 9 times the integral. Notice I'm not doing any calculus yet. I'm just doing some algebraic manipulation. Okay, so I have my x doesn't have an automatic substitution. X squared plus 1 gets replaced with a u. Dx gets replaced with du over 2x. And then I'll just carry along this minus 3 tan x. Okay, what do you notice about the x's here? They cancel. So 1 on the top, 1 on the bottom, the x's cancel. I have a 2 in the denominator. It's a constant, so I can pull it right out of the integral. So this becomes 9/2, right? And the 2 stays in the denominator when you pull it out, so it becomes 9/2 times the integral of 1 over u du. I have not taken any antiderivatives yet. All I've been doing is replacing one variable with another variable. Yeah, in the integral that we're working on, we haven't taken any antiderivatives yet. Now that I have only u's and no x's, I have changed everything to u's, right? Changed everything to u. At this point, now I can try to take an antiderivative. Do I know a function whose derivative is 1 over u? ln. So it is, we have 9/2 times the ln, it's actually the ln of the absolute value of u, plus c, minus, we'll call this c1 because it's maybe different than the other c. All right, finally, last step, replace the u. After you've done your antiderivative, replace the u with the x again, with what it equals in terms of x. So I have 9/2 times the ln of the absolute value of x squared plus 1. And then I'm gonna combine my 2 arbitrary constants. They're like terms, they're both just constants, so combine them into a third constant that's arbitrary. Arctan x plus some c. We'll just call it regular old c. That's fine. Yeah, Justin? No. Oh, yes, because in this case you could, because when you square something, you always get a positive. Yeah. Yep. Right. Okay, so what made this method work, right? The key step that made this method possible was the canceling step, right? Because we were able to change everything from x's to u's. If the x's hadn't canceled, I would have just made the problem worse. I would have had an integral with x's and u's in it, and it would have been even worse, right? So what made it work was the canceling. So if you want to choose your u wisely so that you end up getting all your x's to cancel. And the way you do that is you look at your original integrand. Okay, so you go look at your original guy here, x over x squared plus 1. You want to choose your u to be the most complicated thing possible whose derivative also shows up in the integrand. Okay? So the reason I chose x squared plus 1 to be my u is because 2x is its derivative, and there's an x in my integrand. So it can differ by a constant coefficient because you can just pull constants right out of integrals, right? But you want to have like the same basic kind of function to try to get a cancellation. So I chose u to be x squared plus 1 because its derivative was 2x, and there's also an x in the integrand. All right, so I'm going to take you back to the u substitution step-by-step walkthrough at the beginning of the packet. We won't go through all the steps together, but you should do that on your own, and know that you're allowed to have this page with you on when you do tests and quizzes. Okay, so let's see, we're on page 59. We're going to go back to the beginning here. U substitutions step by step. Let u equal some stuff in terms of x. Okay? It may take several guesses to choose a correct u. That's totally normal and okay. If you choose a u and it doesn't work, you might try another u, right? A basic guideline is to choose a u whose derivative also shows up in the integrand. Okay, find du dx and then solve for dx. Rewrite the integral by putting u instead of the stuff and replacing dx with what it equals from step 2. And then cancel, 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 simplify, simplify, simplify. And here's a really important step. What's left after you've canceled and simplified should only be u's. Okay? If there are any x's that didn't cancel, you might have to consider a different choice of u or try a different technique. Then integrate with respect to u, then replace u with the stuff, and then you can always check your answer by taking its derivative and making sure you get the integrand back. Here's some hints for choosing u. Let u equal the stuff in each of the following cases. Okay, it's typically the inside part of a composite function, but not always. Okay, so again, there are no hard and fast rules as to when a u substitution will work. Sometimes there's some trial and error involved in the choice of u. Yes? Nope, you're going to solve for dx because there's a dx in your original integrand and you want to replace it with something. So you solve for dx so that you can make a substitution. Yeah.
You have like du equals some expression times dx.
You could, yeah. Okay, so there's often some trial and error involved in the choice of u. That is normal and expected. Sometimes you just can't see ahead of time what u will work, and you might have to try 2 or 3 things before you get it to work. However, this technique doesn't always yield a tractable integral. That is something that we can take an antiderivative of. If you end up with both u's and x's in an integral after you've substituted, the u substitution you tried typically won't work. So for example, if I want to find the integral of 2x times the sine of x to the 4th dx, what do you want to try for u, you think? X to the 4th is a great guess for u. So if we let u be x to the 4th, and that means du dx is 3x cubed, which means that dx is du over 3x cubed. So we come back over to our integral, and we substitute everything that can directly substitute. So I've got 2x times the sine of u. Oh, sorry, 4x cubed. So I have 2x. That doesn't have a direct substitution, so I just leave it for now, and fingers crossed that it cancels. Times the sine of u, and then times dx, which is du over 3, why do I keep doing that? 4x cubed. Okay, so I've made all my direct substitutions, and now I'm going to cancel whatever I can, right? Hoping that all the x's go away. But they don't, right? This one cancels with one of these, right? And they don't all go away. And I've just made the problem worse now, right? Now I have x's and u's in here. They don't all go away. So u substitution just won't work in this problem, right? If instead of 2x, if I had an x cubed, something x cubed in that spot, this would have worked because then I could have gotten a cancellation, right? So if you see an x to the 4th and an x cubed, you go, oh, x cubed is like a derivative of x to the 4th. That's a good sign that u substitution will work. So it doesn't always work on the first attempt. If at first you don't succeed, you are not necessarily a failure, right? In this one we just tried, we are, right? We could try u's all day and it just, we'll never get it to get rid of all the x's. But you should definitely try like at least 2 or 3 things before you give up and say U substitution doesn't work. All right, try some on your own.